Oh, there's light now.
So welcome. Today we're going to be talking about data processing and open source. In particular, how Google is helping shape the future. So my name is Frances Perry, and I'm a data processing infrastructure geek. I love figuring out the right way to take a really complex and powerful data processing system and make it extremely intuitive and easy to use.
Good evening. I'm James Malone. I'm a product manager here at Google. I'm fascinated by data because data is everywhere. I'm also really passionate about open source software because I think it shows what people can do when they work together to collectively solve really challenging problems. What's really interesting to me is when they can work together, both data and open source. So today we're going to talk about the next generation of data processing. We're going to go boldly where many have gone before with mixed success. What we want to do is we want to lay out a meaningful vision for open source next generation data processing. We'll start by looking at now, challenges today. The challenges that exist today that should not exist tomorrow. We'll then launch into MapReduce and its influences on the challenges of today and how it sets the stage for next generation data processing tomorrow. Next, we'll look at solutions that exist inside of Google right now that can help you solve data challenges. And finally, we'll talk about something that's new and exciting, Apache Beam, how Google can bring its experience and work with the open source community to solve next generation data processing problems. First, let's create a foundation. Let's frame the discussion of next generation data processing. So I work in Seattle, and Frances and I were given a template, and the slides may look somewhat familiar at this point in the day. And I had one thought when I saw this slide: I don't have enough vitamin D, and I am definitely working in the wrong Google office. I absolutely want to work there. It's gorgeous. But if I were you, what I would be wondering is, we're talking about next generation data processing. What things specifically, what challenges do we need to solve for in order to end up in a space where we can say we are in next generation data processing? We think there are three specific things. Now, infrastructure can sometimes be hard. Now, creating unified batch and streaming data processing pipelines can be challenging. Now, the portability of those data pipelines can be a real pain. First, management. Now, the emergence of open source data processing tools that allow you to process large amounts of data in parallel, the Apache Hadoop and Apache Spark ecosystems are a great example. They're both a blessing and a curse. They allow you to set up an environment where you can decide on a tool, you can read the documentation, you can get your infrastructure, you can then set that infrastructure up, you can set up your tools, but then you have to tune the tools. You often have to find experts who can help you adjust all of the knobs on those tools. You have to productionalize your environment. Even though the tools exist, and they're awesome, they're very powerful and they're great to use, they can be very difficult. And by the end of the day, you are probably now a team of people supporting both infrastructure and software, when your end goal at the end of the day was to simply process a lot of data that's important to you. But next, this should no longer be the case in the future. We think it should be very similar to using a tool in a toolbox. You should be able to open a toolbox, pick out the tool you need, not have to assemble the tool and forge the iron and tune everything. You should know how to use the tool intuitively, or even just watch a simple YouTube video to get it, and then carry away and solve your problem.
Now, the second thing that we think is really important for the future of data processing is the right set of abstractions. How you represent your data processing pipeline. Right? As data processing needs to become more sophisticated, users often find that they have to write a traditional batch system for correct results, and also use a different streaming system to get more real-time updates. Now, this bifurcation means that you have to write twice as much code, you have to maintain twice as much infrastructure, and somehow reconcile these two different results into one conceptual output. Now, we think if we can find the right way to represent our data processing pipelines, we can handle both batch and streaming use cases in the same unified system. And the final thing that we think is going to change the future of data processing is portability. right? Many current systems tightly couple the code for expressing your logic with the implementation of the service itself. So that means if you want to move your application from Hadoop to Spark or from on-premise to cloud, you have to rewrite large portions of that logic in a different framework. And then you have to dive in and find what the right tuning knobs are in this new scenario. So we can break that cycle. Again, if we find that right abstraction, that right model, you'll be able to write your application logic once and run it in multiple places.
So ultimately, you might be asking, great, so you've identified three things: management, model, and portability. But why do these matter? Why are these the things that you have picked? Why are these the problems that we need to solve for? And what are the impacts on me today and in the future? I'm going to use a metaphor. Say you have a rental car, and many of you may have gotten a rental car when you traveled here. You trust that the rental car agency has managed the car. You don't have to pop the engine or pop the hood and check the oil level every time you get a new rental car. You also are familiar with the controls of a car, so you don't need to learn a new set of controls every time you get a rental car. And while you're traveling in the United States, most signs are relatively the same, and you trust that the car will drive on different types of roads. So you have the portability. You can drive on the freeway, you can drive on country roads, you can drive on city streets. There's no problems there. Ultimately, why it matters to you is when you are wrangling with the infrastructure and the tooling to solve complicated data problems, you are focusing on the infrastructure and the tooling. And you're not focusing on what matters to you the most, your data. These are not new challenges, and in fact, a lot of these challenges have existed for quite some time. They're really hard problems to solve, however. So let's start with a little history, because MapReduce is a solution to some of these problems which has influenced the present and potentially the future.
All right, so back in the early days, Google, like many other folks, needed to process a lot of data. However, conventional tools and methods couldn't keep up with the growth of this data. So engineers ended up spending their time writing custom computations to handle each particular use case. Now, if there's one thing engineers hate, it's wasting time, right? Particularly on something that can be automated. So the engineers started looking for a generalized solution for specifying logic that runs in parallel across many machines. At the same time, they wanted to shield the author of that logic from dealing with low-level details, like moving data from one machine to another and handling fault tolerance. So Jeff and Sanjay settled on a simple reusable pattern, right? You take your data set and you partition it into chunks. Then you take each chunk and hand it out to a different mapping machine. A mapping machine takes its chunk and runs a piece of user-provided logic over that chunk to process each element. Now, each of those chunks is processed independently on a different machine. So this makes it extremely easy to parallelize. Once the mapping machines are done, they redistribute their data across multiple reducing machines based on a key of the data. And then finally, each reducing machine, again, independently from other reducing machines, runs another bit of user logic to create these final outputs. Together, this is your output collection. Right? Now, the beautiful thing about this pattern is it's extremely powerful. You can take pretty much any big data processing algorithm that you want, and you can run it in MapReduce. You might have to take your algorithm and completely convolute it beyond any recognition, but you can shove it into that framework if you try hard enough. So in 2004, Google published a paper on MapReduce. And at this point, things diverge a little bit. Inside Google, we kept innovating. But we were doing this in a relatively homogeneous environment. So we had only a few file formats we were dealing with. We had a limited number of languages that we needed to support. And we had extremely standardized tooling. So this meant that we got to spend our time focusing on really refining our core methodology and generating new ideas on how we would want to process this data. So we continued to publish papers on these new ideas. And from the external community, folks saw a lot of PDFs popping up. Right? A lot of good things to read, but nothing concrete that you could actually get your hands on and play with. Now, at the same time, externally, in the open source community, we had a different implementation of MapReduce inside Hadoop. Right? And an entire data processing ecosystem developed here. Some of this continued to be published by the Google papers, but there was also a lot of new innovation that happened here on its own in this very diverse system. So today, Google Cloud Platform contains two systems, two products that come from this MapReduce lineage. The first one is Google Cloud Dataflow. And this is a fully managed cloud service that evolved directly from MapReduce and includes some of these later ideas from Google, like Flume Java's clean abstractions and Millwheel's focus on streaming and real-time execution. Now, for those users who have a significant investment in open source technologies already, we have Google Cloud Dataproc, which is a fully managed service for executing Hadoop and Spark programs. So James.
Thank you. So let's take a look at the first product in the Google Cloud Platform portfolio that's based directly, quite literally, on MapReduce, Google Cloud Dataproc. So as Francis mentioned, the Apache Hadoop ecosystem evolved directly as an implementation of the MapReduce white paper. And arguably, it's had just, I apologize, unarguably, it has had an enormous impact on the current state and future of data processing. It allows people to solve really hard data problems that weren't possible before. It has the models, it has tools, it has the community. It's really made a change in how people process data. But a lot of these tools also come with their own set of challenges. And this is true for Apache Spark. It's true, I think, for Apache Hadoop. In general, a lot of open source tools share these three common problems. First, installation. They can be a real pain to install and configure. Second, they can be really tricky to run at a cost-effective scale. Third, typically you have to know quite a bit about all of these different components to use them effectively. Well, Google has been running MapReduce and other data processing technologies at scale for a long time. So why not leverage all of this existing investment, infrastructure, and knowledge to create a product? Well, we did. And Cloud Dataproc is the answer to that challenge. It brings the familiar Spark and Hadoop ecosystem to the Google Cloud Platform. This is great for moving existing code that you've already developed in on-premise or other cloud environments, or brand new development. And if you're familiar with the Spark and Hadoop ecosystem, there's a wealth of different tools that fit into that ecosystem. Cloud Dataproc ultimately helps solve the thorniest management headaches that usually follow the Apache Spark and Hadoop ecosystem. It really focuses on speed, simplicity, and cost effectiveness. Cloud Dataproc is designed as an ephemeral solution. And ultimately, what we mean by that is we want you to have clusters when you need them, when you actually have work to do. And we want you to be able to turn them off when you don't need them. We don't want you to have to carry excess idle capacity when it makes no sense to you. So we like to think of Cloud Dataproc as combining the power of Google, both in software and hardware, with the power of open source. So ultimately, what is Cloud Dataproc? It's best to think about Cloud Dataproc as two top-level concepts, clusters and jobs. Cloud Dataproc clusters ultimately are a layer cake of three kind of big components. The first, Cloud Dataproc is built on the power of Google Cloud Platform. This means the virtual machines that you use for your cluster are Google Compute Engine machines. You can connect to Google Cloud Storage. So we use the already existing tools available to us. We then have an agent that runs on top of this cluster. It's really the glue between the underlying Google Cloud services and the open source tools that live on a cluster. The agent is doing all of the things like tuning the 500 to 600 different knobs that exist in Spark and Hadoop alone. And finally, we have the open source tools. This is Spark, this is Hadoop, this is Hive, this is Pig. The second top-level concept in Cloud Dataproc are jobs. And we provide a set of tools which abstract the pain of trying to manage workflows away from you to create an abstraction layer where you can run some of the most popular job types on your cluster without having to open terminal windows or know how Spark submit works, which means you can submit Spark, PySpark, Spark SQL, Pig, Hive, Java MapReduce, all without actually having to ever log into a cluster. You can simply create a cluster in one click and run your job in your second click. That's it. Cloud Dataproc is also not isolated. It doesn't stand alone. And this is a very important point because it means that you can read and write data to many different places. You can read and write data from other GCP products. You can read and write data to Dataproc jobs, both on the same cluster, or since it's an ephemeral solution and you can create clusters quickly, any other cluster. You could also feed data to other applications on the cluster. So we give you the ability to install other open source components, for example, Apache Zeppelin on the cluster, so your Spark could be talking to Zeppelin all in one cluster easily. I want to go to the point about Dataproc talking to other Google Cloud Platform products, because this is a very important point. It allows you to use the familiar Spark and Hadoop ecosystem that you may already have knowledge, existing code, documentation, tooling, and use it with the other powerful tools in the Google Cloud Platform portfolio. For example, you could have a PySpark job, which reads data from Google Cloud Storage, processes the data with Spark using PySpark and potentially all of your favorite Python libraries, and then output the resultant data set to BigQuery. Google Cloud Dataproc is designed to bring the experience and power of this very familiar ecosystem to the integrated and comprehensive processing platform provided by Google Cloud Platform. I want to back up some of the things I'm saying and not just say that Google Cloud Dataproc is fast, easy, and cost-effective. I want to give some specific points to actually elaborate on why that is the case. So let's start with speed. On average, Cloud Dataproc clusters start in about 90 seconds for your average cluster. They also stop in about the same time. That's really important because if you have an ephemeral cluster that you're creating precisely when you need it, it means you spend less time waiting for your cluster to become available. You also aren't paying for your cluster to start and stop. Second, clusters can be resized at any time. So if you have a series of big jobs, you can add more nodes. When you're done, you can remove the nodes. And Cloud Dataproc will handle all of the brokerage and trying to commission and decommission nodes without causing your jobs to fail. We also don't bloat the clusters. So we include vanilla versions of Spark, Hadoop, Hive, Pig, and a few other components. But we're not putting on software extras that we think you might not need, which are going to slow the cluster down or just complicate your use of the cluster. Ease of use. So as I mentioned when I was talking about jobs, we provide a job wrapper which allows you to send jobs to the cluster, monitor jobs. You can stream the output of drivers without ever opening an SSH window. You can do it in a browser. You can do it with Python. You can do it with any number of libraries. You can do it through a REST API. That also means we have several surface areas that you can use to interact with Cloud Dataproc, including our Google Developers Console, the Google Cloud SDK, REST APIs, and at the end of the day, since this is built on Compute Engine and it is vanilla Spark and Hadoop, if you want to go SSH into clusters, go wild. You totally can. And finally, optimized for cost. I have never really met a Spark or Hadoop job which runs specifically to 1 hour or 2 hours or 3 hours. Typically, it's a fraction or a subset of hours. We bill Cloud Dataproc by the minute with a 10-minute minimum. This means that if your job runs for 28 minutes, you pay for 28 minutes, not 1 hour. And when you're creating large clusters with potentially tens or hundreds of nodes, this can be absolutely substantial. We also priced Cloud Dataproc based on the size of your cluster and the number of virtual CPUs, so it's easy to understand, and doing the cost calculation is fairly straightforward. And finally, you can use preemptables and now custom machine types as part of our GA last month that allow you to very carefully craft the size of your cluster based on the needs of your data processing pipeline. That means that you can articulate your cluster specifically so you aren't over or under consuming resources. So going back to the three things that Francis and I are discussing today that are really important problems that need to be solved for next generation data processing, Cloud Dataproc addresses one of them head-on, management. We have really tried to solve the thorny management problems that exist with some of the open source tools so you don't have to worry about them. But there are other services in the Google Cloud Platform portfolio that go a little bit further, and Cloud Dataflow is one of them.
All right. Thanks, James. So let's dive in to more details on Cloud Dataflow. Now, this is the path that came out of MapReduce and is based on a bunch of continued innovation internally at Google. Now it's available to you as a cloud product, and there are two key advantages to Cloud Dataflow. The first benefit is the programming model. This is the way that we encourage you to write Dataflow programs. This is the way that you represent your business logic, and you focus on that, your application logic, not how you cram that logic into some underlying infrastructure. Right? Instead, you're building a pipeline. Your pipeline contains a mix of custom element-wise processing, aggregations, and library functions. Dataflow pipelines can process both bounded, fixed-size data sets, like we're used to in traditional batch systems, but it can also handle infinite streams of data. And when you're writing that application logic that becomes your Dataflow pipeline, you don't have to wonder about what type of collection you're running over. Your logic will apply equally well to both bounded and unbounded data sets. This means that you have a lot of flexibility in how you write your logic, and it can be reusable in many different scenarios. Now, to truly unify batch and streaming into a single system, we need to separate the notion of event time from processing time. Event time is the time an event actually happened. So let's say we have a mobile gaming application. Users are on their cell phones all over the world, frantically doing something. They're popping balloons, crushing candy, I don't know. Whatever it is they're doing, it's happening everywhere. And we want to process those points that they're scoring and figure out information about that. So the time the user crushed the candy, that's the event time. The processing time is the time when that score is available in our system for processing. Ideally, those would be the same thing, but distributed systems never cooperate. So there's actually usually quite a difference. So here, we've got a sample data set of points that a specific team scored in our game. So on the x-axis, you can see the event time. Again, this is the time the point was scored. And on the y-axis, we have processing time. So if distributed systems weren't actually a problem, right, everything would appear along this dashed line. Something would happen, and immediately we'd be able to process it in our system. Sometimes things aren't so bad. So this event here happened right before 1207. And just after 1207, it's available in our system for processing. So maybe there was just a small network delay. Other times it's worse, though. So this event over here is 7 minutes delayed from when it happened before we can process it. Perhaps this user was playing our game in an elevator or in a subway, somewhere where they had a temporary lack of network connectivity. We had to wait for this user to reestablish a connection before that event was able to be ingested to our system and processed. Now, the margins of this graph aren't nearly wide enough to contain what would happen if our game supported an offline mode. Right? Now we could have users playing our mobile game on a transatlantic flight while they're in airplane mode. It might be hours until the users land, reconnect, and those events are available for processing. So as you can start to see, these types of infinite out-of-order data sets are really, really tricky to reason about, unless you know the right questions to ask. So the Dataflow model itself revolves around 4 key questions. The first one is, what results are calculated? What is that algorithm that you're actually doing? Are you computing sums, joins, histograms, machine learning models? Where in event time are results calculated? So how does the time when each event actually occurs affect your overall results? Are we aggregating events over all time, for fixed windows of time, or based on bursts of user activity? When in processing time are results materialized? So that's asking, does the time each element arrives in the system and actually get available for processing, does that affect results? How do we know when to emit results? What do we do when data comes in late and we've already emitted the result? And finally, the fourth question is, how do refinements relate? So if we start emitting multiple results because new values are coming in and we're changing our mind, what do we do with each of those new copies? How do they interact? So let's take a look at how we use these questions to build a simple pipeline. So here's a snippet from our pipeline. We are processing those scoring results from our mobile gaming application. In yellow, you see the computation that we're performing, the first question, the what, right? Here we're taking team score pairs of these scores that happened, and we're going to sum them per team. We want to find out the total score per team. Okay? So right now, this is a pretty simple pipeline. And let's see what happens if we execute it. So in this looping animation, you see our axes of event time and processing time. And that gray line represents processing time as it progresses. As the pipeline executes and encounters elements, they're accumulated into that intermediate state shown as in white. And finally, when processing completes, we emit the result in yellow. So this is just how a batch pipeline would execute. It's pretty standard. But as we address in the next few questions, this is going to get more powerful. The first thing we're going to play with is this notion of event time. So we'll start by specifying a windowing function. And by doing this, we can calculate independent results for different slices of event time. So we could compute something for every minute, every hour, every day. In this case, we're going to use 2-minute chunks of time and ask for a different sum per team every 2 minutes. So now, if we look at how things execute, you can see that based on event time, we're calculating 4 independent results. Every 2-minute slice of event time is going to give us a different result. Now, at this point, we're still waiting for the entire computation to complete before we emit any results. And this works OK if we're dealing with a bounded, fixed-size data set that will eventually finish processing. But it's not going to work if we're processing an infinite amount of data, right? Because we'll never actually complete and produce results. So there, what we need to do is reduce the latency of individual results. And we do that by asking for results to be triggered based on the system's best estimate of data completion. We call this estimate the watermark. It's the way the system estimates that at this point it's pretty much seen all the data it's going to see for this portion of event time. So now I've drawn the watermark on our graph in green. Right? And you can see that as the result for each window passes the watermark, and we think, well, we pretty much got all the data, we go ahead and emit the result. But again, this watermark is just a heuristic. It's the system's best guess about data completeness, and guessing in a distributed system is going to be a bad idea. Right now, the watermark is too fast. We're moving on before we have all the data. So in that first window, we thought we were done. But then that user who was offline in the elevator finally reconnects, and we realize we've got some late data. And it just gets missed in this case. That user's out of luck. Their team is never going to benefit from that score. Now, we could be slower and more conservative with our watermark. But if we do that, we might have to wait an unrealistic amount of time. So if we're dealing with those offline users on the airplane, we're going to have to wait till every flight everywhere lands, just in case there was somebody in seat 26B who was playing our game. Right? So that's not reasonable either. We need to be able to deal with this type of heuristic best effort watermark and work around it. So we do that by using a more sophisticated trigger. So now we're requesting both early speculative firings. So as results are trickling in, we're asking for tentative updates as we go. And also, we're asking for late firings or additional updates if we see events later than we expect. So what this means, though, is that we're going to be seeing multiple results for that same slice of event time. And now we have to answer our fourth question. How do those results refine over time? In this case, we're going to use accumulation mode and just continually accumulate the score. So every time we see new results, we'll emit a new cumulative sum that just continues to grow. Now we go back to our graph, and you can see that we're getting multiple results for each slice of event time. In some windows, like the second, we produce some early speculative results as data is still arriving. Then in every window, as the watermark passes, we think we've pretty much seen it all, and we emit an on-time result. And finally, if there are late results, like in that first window, we might emit a late updated element. And because we chose to accumulate, each result that we emit includes all the elements for that window, even if those elements were already part of a previous result. All right. So what we did here is we took an algorithm. In this case, it was just simple integer summation, right? I could have taken a more complicated algorithm, except then I would have had to animate it, and these already got complicated enough. So we just did integer sums here, but it could be a much more powerful chunk of user application logic. And then we tweaked a few lines. And by changing those other questions and addressing them, we were able to cover a whole number of use cases. We went from traditional batch all the way up through advanced streaming without having to change anything about our algorithm, the what that we're actually computing. So just like MapReduce fundamentally changed the way that we do data processing by providing a new set of abstractions that allowed us to reason about these types of programs, we think this Dataflow model will change the way we do batch and streaming processing in the future by unifying them together based on these 4 questions. So that's the first benefit of Cloud Dataflow, the programming model and the way that you write your pipelines. The second part is the fully managed service for executing these pipelines. This service scales the number of workers and configures that throughout pipeline execution as your data sizes evolve. It dynamically schedules work across your different machines, and it provides integrated monitoring and logging. So there, between those two, between the model and the fully managed service, we've addressed 2 of our 3 goals, but we still want to address portability. That's where Apache Beam comes in. So in late January, we took the Dataflow model and the SDKs that implement it, and we developed these in conjunction with the managed Dataflow service. But along with some partners, we took this programming model and donated it to the Apache Software Foundation as the incubating project Apache Beam, which means, among other things, we get a new logo. So here's our snazzy new logo with 2 overlapping beams of light representing the unification of batch and stream into beam. And now we have puns all over. We're beaming with joy. There's all sorts of, the puns never get old. All right. But what does Apache Beam actually include, right? So it's the programming model, this idea of describing your data processing in terms of the what, where, when, and how. It's the initial Java SDK that we developed as part of Cloud Dataflow, and there'll be other SDKs, including Python, to follow. And most importantly, for portability, it's a number of runners that know how to take a Beam pipeline and execute it on an existing distributed backend. So right now, that includes runners that can run a Beam pipeline on Apache Flink, Apache Spark, and then, of course, the Cloud Dataflow service. Our goal, as we transition the Dataflow programming model into Beam over the next few months, is to fully support 3 different categories of users. We've always focused on end users. These are the users who want to write data processing pipelines. They want that nice little Pac-Man from the beginning, right, where they focus on their logic and their results, and they don't have to deal with the other stuff. Right? They just want to take the language that they're already familiar with and run it in whatever distributed processing environment is most convenient for them. But in addition to those users, now as part of Apache Beam, we want to focus on developing stable APIs and documentation that are going to allow others in the open source community to develop new SDKs and provide new runners for alternative distributed processing environments. So we're just getting started growing that community.
So building a community around Apache Beam is going to be absolutely critical to its success. The community will help Apache Beam really achieve the goal of being an open source platform for next generation data processing. But building a community involves a few key things, and we're just getting started building this community. First, we have to focus on collaboration. We were really surprised when we wrote the Apache Beam incubating proposal and submitted it. There was an outstanding amount of interest in Apache Beam. There's also a lot of groups that have thrown in new ideas and ways that they want to expand Beam and see Beam grow. Taking all of this and collaborating together so we can take all of the collective energy and brain power and needs and problems that people want to solve and work together towards a unified solution is going to be both a challenge, but ultimately incredibly rewarding. As Francis mentioned, the Dataflow SDK and model at this point has really focused on end users. We want Beam, through the collaboration, to also include the SDK writers and the runner writers. Now, we want to grow Apache Beam. And there's a few people that may be wondering why the Apache Software Foundation. It's come up in conversations that I've had with people here. Ultimately, Apache Beam is a great fit for the Apache Software Foundation because it will grow within a community of other data processing tools. So as Francis mentioned, there's a Flink runner and a Spark runner. It's not all about just making Apache Beam awesome and better. There may be things that we need to help out on with Spark or with Flink or other projects. And as a member of the Apache software community and under that umbrella, we can make that happen. And that's critically important. We also want to learn. And this is Google's first data-related contribution to the Apache Software Foundation. And we're learning quite a bit. We're learning the Apache way. We're also shifting from Google tools and infrastructure to those that are used by Apache projects. And we're trying to take that learning and apply it and learn quickly and get started quickly and move things forward. So we wrote the proposal in January, and we entered incubation to the Apache incubator in early February. To show how serious we are about really getting started and making an impact and moving things forward, the first commit to the repository was in late February. So we're really excited to get moving. Early in 2016, so where we are now, we're really focused on refactoring and redesign. We really, really want to focus on all three of those use cases, so the end users, the runner writers, and the SDK writers. That means by mid-year, we're going to take all of the design and refactoring and things that we've come up with, new APIs, and we're going to be implementing them on the Beam project. It's important to note, though, that we don't want to and we will not interrupt Dataflow users during this process. So we're really focused on improving and making these updates to the Beam project. So towards the end of the year, the Beam team can say that Beam pipelines will run on multiple runners. You could take a Beam pipeline and run it reliably on Flink or Spark. You could also use the Beam SDK to articulate Beam pipelines and run them on the Cloud Dataflow service. So with Beam and Cloud Dataflow, you start to check all of the boxes for next generation data processing. With Cloud Dataflow, you get an awesome managed service where you can send it pipelines and you don't worry about infrastructure. You don't worry about spinning up servers. You don't worry about logging and monitoring. With Beam, you get a portable, powerful, unified model that you can use to articulate data processing pipelines. So between the two, you start to end up in a place that is truly next generation. That said, while we think that Cloud Dataflow is going to be an awesome place to run Beam pipelines, and we think it will be the best managed way to run Beam pipelines, Beam itself is also portable, which means that there are other runners that you can use to run Beam. And these runners can exist in any number of environments. They might be on-premise. You might want to run Flink, for instance, on a cluster in your local data center. You might want to run Spark on another cloud. That's OK. These runners may have varying levels of fidelity in how they support Beam based on their own models and underlying semantics. But again, going back to my comment about being a member of the Apache Software Foundation, that's why it's very important for us to work together inside of the Apache umbrella so we can try and help everybody out and move everybody forward. Now, it's getting late. And if you only remember a few things from this, we've been talking for a while. If you wake up tomorrow and you're like, that was the best presentation I've ever seen, please remember it with the following points. First, the MapReduce paper in 2004 kicked off a flurry of activity. You had two branches that predominantly emerged. You had one in Google that continued to iterate on the ideas of MapReduce and create new papers. And then you had a whole ecosystem develop in the open source community. As a result of these two branches, we have two awesome products that you can use today in Google Cloud Platform to take advantage of the work in these two work streams. You have Cloud Dataflow to take advantage of all of the awesome iteration in both infrastructure and software that Google invested after MapReduce. And you have Cloud Dataproc to take advantage of all of those components you could use on Cloud Dataproc today. Apache Beam is a bridge between these two work streams that split in 2004. In 2016, we want to bring them back together. Apache Beam can be managed. Using services like Dataflow, it's very easy to run Beam on managed services. Beam provides a unified model for batch and stream processing. Finally, Beam pipelines are portable along different runners. You can take your Beam pipelines and run them on different runners in different locations.
Am I on? There we go. We hope this talk leaves you wanting to learn more about doing data processing and open source at Google. You can go use Cloud Dataproc today. You can start spinning up Hadoop and Spark clusters and use that fully managed service. If you want to learn about the Dataflow and now the Beam model, you can use Dataflow today to write pipelines that run on Cloud Dataflow. And over time, as we finish bootstrapping, you'll be able to use Apache Beam to run those same pipelines anywhere. All right, well, thank you very much. James and I will be around, so please come find us, ask questions. Thank you very much.